Yeah. Well, I mean, it depends on who you are. Like people still recognize you, but you do look very different with your glasses off. So, but yeah, just continue wearing your mask until things die down, and they're like, hey, don't wear your mask, and you'll be fine. Wash your hands. Do the things you're supposed to be washing your hands anyways. It's a good thing to do. It doesn't hurt anything. Like we've been apparently drinking gross pond scum water in the teacher's lounge for who knows how long. And obviously it hasn't killed me or made me sick, but now that I know about it, am I going to continue to drink the gross pond scum water? No, I'm going to stop drinking it. No, that's not what's happening there. No. Hey, I do plenty of things that build my immune system. I don't need to drink dirty, disgusting water to do that. So, that's up to you. You can take notes or not take notes. I'm not going to force you to do nothing. But what we have today is we're starting on fission and fusion. So, this, actually, I'm going to leave the lights on. So I need to turn them on. I got to get used to that. I like to have the lights off, but y'all fall asleep too much. And I've got a new tool in my arsenal. If you fall asleep, no, I'm gonna wake you up with my air horn, which never runs out of air. It's actually pretty loud. Yeah, wake you up with the air horn, and then you're gonna have to stand up for the rest of the presentation. So don't make me air horn you, because that's what's gonna happen now. Yeah.
Can you do it with textures too?
What?
Can you do it with textures too?
Textures? Like you text the phone up?
Yeah, I'm just gonna take your phone from you. So keep your phones away. Don't. What is it? $15 or $20? Don't make your parents pay $15 to get your phone back. They've already paid enough. Yeah, that would be cool, but that's probably not ever going to happen. But we'll just leave the option open because I do have really good reflexes. Well, you never know. But I'm probably not going to walk close to you because again, I don't want to be like all up in your midst. I'll stay back here and hope that the front row doesn't have COVID. All right, so listen. Hey, all right, let's refocus. What we're doing today is fission and fusion. So we've been talking about nuclear radiation. We've been talking about what nuclei do when they're unstable. And now we're going to talk about fission and fusion, which is how we create nuclear power plants, nuclear weapons, and hopefully one day nuclear fusion, which will be a really low cost, high energy production thing that doesn't have very much pollution associated with it. Now, we'll talk about nuclear fusion, but I just want to start off with saying we've always been 20 years away from getting nuclear fusion. 20 years ago, we were 20 years away. And 20 years before that, we were 20 years away. And you can probably find a news article written today that's like, we're really close. We're about 20 years away from getting nuclear fusion. It might be something that we can never, ever do. We are closer now than we ever were before. But essentially, you have to recreate the inside of a star, like the sun. You have to recreate it like in a lab, in a safe place in a lab, in a tiny little like magnetic container. And so we might not ever get to the point where we can do that efficiently, where it actually produces more power than we put into it. But we're going to keep trying forever, probably. So either it happens or it doesn't happen. Don't hold your breath on that one. But today we're going to talk about fission, which is more practical to use as opposed to fusion, but we will talk about both. So, and then we have a little assignment. I think it's like 8 or 9 questions, not too bad. So fission and fusion reactions occur naturally. They don't need humans to make them happen. Now, as with all things that occur naturally, we kind of take control sometimes and we produce them for our own means. So we do fission reactions to create electricity. That's what nuclear power plants do. And in fact, in a little bit, I'll pull up on the map the closest nuclear power plant. Does anybody know where it's at?
Didn't one blow up a couple years ago?
No, not Russia. We have nuclear power plants all over the United States. And yeah, they blow up sometimes, but they're getting generally safer. There's one down in Glen Rose. If you've ever been to Glen Rose, I don't know if y'all play Glen Rose in sports or if they're bigger. Yeah, it's not that far down. It's like what, a couple hours south. They got like a Tres Rios where you can tube the river, or They've got like a little park where you can go see dinosaur prints in the sand and fossils and stuff. So, yeah, down in Glen Rose, they have a nuclear power reactor, kind of like the one that Homer Simpson worked at. And they produce energy by using radioactive materials and the process called fission. So obviously we can start these artificially and use them for our own means. What happens in a nuclear reaction? Your mass number and your nuclear charge are conserved during nuclear reactions. So we're not creating anything new. We're not getting rid of anything. We're just kind of rearranging the formation of these nuclear substances. There we go. So the total mass of a nuclear reaction is not conserved. You do have some energy leave because E equals mc squared, right? What's the E stand for? Energy, and it's on the other side of the equal sign as the M, which stands for what? Mass. So energy can actually be converted from mass. You can turn mass and turn it into energy, which is what E equals mc squared is kind of all about. So small amounts of mass is typically lost in a nuclear reaction due to slight differences in masses of protons and neutrons before and after the reaction. So there you go, E equals mc squared. I must have remembered that from the previous year. And C, as we learned before with the electromagnetic equations, C is the speed of light. So energy is equal to mass times the speed of light squared. So small differences in mass creates large amounts of energy. That's where we get the energy from these nuclear reactors and these fusion and fission equations or reactions. Amounts of energy produced during a nuclear reaction is larger than a chemical reaction, which is why we're not just mixing chemicals to create the heat. We're using a nuclear reactor to create the heat. So fission. Does anybody, just before I explain it, does anybody know the difference between fission and fusion? If I'm fusing something, what am I doing? Putting it together. So fission is going to be what? The opposite. Yes. And that's essentially what it is. Fission, you're breaking things apart. You can kind of think of the word fissures, like cracks in the ice or cracks in the ground. It's actually split open. Where fusion, like if you're melting two pieces of glass together or something like that, you're fusing things together, putting them together. So fission is a nuclear reaction with a nucleus of a large unstable atom. So you got to have something big like uranium, plutonium, something large and nuclearly unstable. The atom splits into two smaller nuclei. Their example, which they don't give you the actual element right here, but you have a big unstable nuclei. You throw in a neutron, which makes it even more unstable. It starts to decompose and actually splits into two different nuclei and splits out a couple more neutrons over here, which, by the way, can go to something else and create another reaction, which we'll talk about in a second. So the fission of uranium into krypton and barium. Here's your uranium. You add a neutron. It makes it even more unstable. It very quickly decomposes into two separate atoms, krypton and barium, and it spits out a couple more neutrons in the process, which each of these neutrons can go and restart another uranium atom and get it to split as well. In that split, you release a little bit of energy, more than a little bit, but not like a huge, huge amount. So you release energy, and that energy is what we're using to power other things. Now, it's kind of difficult to get that done, so we'll talk about how we do that in nuclear power plants. So what we call this is a chain reaction, because the thing we used to start it, which was the neutron, we create 3 more neutrons. So as long as I have more uranium, this is just going to keep going. Each of these neutrons is going to start another reaction, which is going to create more neutrons, which is going to start more reactions, and it's just going to like kind of snowball into this huge chain reaction, which if you think about it, is kind of like dominoes. You have the whole line of dominoes. You just tip one of them over, and each one knocks over the successive one and just keeps the whole chain going. So a chain reaction is a reaction in which the products from one reaction are used to start another reaction. So we create neutrons, we start it with neutrons, and it just keeps happening over and over and over again. In fission reactions, those free neutrons that are released as products can start additional fission reactions. The number of reactions and the total amount of energy released increases exponentially. So if something increases exponentially, what does that look like on a chart?
Super. Right. Oh.
So we're going to start down here. We don't have any energy.
Drastic.
We started off, and what's it going to do?
Skyrocket.
Yeah, it's going to go up. It's not going to go up in a straight line. Exponentially means you start off kind of slow, and then you eventually go up, and you kind of have a curve. That's an exponential curve. And y'all should know this from math class. And so this is an exponential curve. You start off small. One reaction is only going to be able to make a couple more. But as each of those start to do more and more reactions as they create their new neutrons, you're going to get more and more and more until all of a sudden you have hundreds or thousands or millions of reactions happening in a very short period of time. So here's a little video to show you the chain reaction. So you start with one neutron and one uranium atom that's actually going to be decomposed. And you can see quickly you start to get this reaction happen. So you go from 1 to 2, 2 to 4, 4 to 8, 8 to 16, 16 to 32, and it just gets bigger and bigger and bigger. That's exponentially. So like a square, you're gonna double your number every single time, no matter how big your number gets. Oh, it just did it again. I didn't mean to do it again. So chain reactions can either be controlled or uncontrolled. If it's uncontrolled, that's a problem. We're creating this. We're using this for our own means. We're trying to get energy out of it. An uncontrolled reaction in a nuclear power plant is going to be what, Garrett? That you mentioned before, or anybody else?
Chernobyl.
Yeah, Chernobyl. It gets out of hand. Things get too hot, and it gets uncontrolled, and it literally starts to melt down the building around it. Another example, which y'all probably don't remember, the Japan tsunami, the Fukushima reactor. The tsunami hit the nuclear power plant. It didn't damage it too bad, but what it did, it knocked out its power and the backup power generator. And so they lost the ability to control that fusion reaction. And in the process, the material heated up so much, it literally melted the building around it. And it took them years and years, like over a decade, to be able to clean that up. And they're still having problems with it today. Last week, I saw an article that they were releasing some water that they had cleaned all the nuclear waste out of back into the ocean. And it was somewhat controversial because they're like, did you really clean it all that well? But Japan does a pretty good job with it. I don't know that they would do that if they didn't think it was nice and cleaned up. So in a controlled fission chain reaction, some of the neutrons are captured before they initiate other reactions, slowing down and controlling the reaction. And we do this in our nuclear power plants in a very specific way. So what we have, control rods. Control rods are your nuclear material. We keep them in water, essentially. The water is like, I think it's called a heavy water. And it helps slow down the neutrons, and it helps absorb them. We also have, well, not the control rods. You have rods of your nuclear waste, essentially, not your nuclear waste, your nuclear material. Sorry, I'm using the wrong terms. Your nuclear material, and then alongside them, you have control rods that are used to absorb that excess neutron so that the heat and energy output of the power plant can be regulated. And you'll actually see them like lowering the rods down into the water to kind of slow down the reaction or pull them up. And that's what happened in the Fukushima plant. They weren't able to control the water level or lower the rods because they had both of their power sources knocked out. And so it actually got too hot in there and destroyed all the material, and there's no way that they could recover the plant. In uncontrolled chain reactions, the reactions continue until there's nothing left to fuel more reactions. It just kind of burns itself out. That is used in nuclear weapons. It happens much, much faster, and it's a much different process than what happens in the nuclear power plants. But it is kind of the same thing that's happening chemically. It's fission that's happening. So now fusion. So we talked about them splitting. Now we're going to talk about them being put together. Fusion is a nuclear reaction where two small nuclei, not big ones like uranium, but small ones like hydrogen, helium, something like that, combine or fuse together to form one larger nucleus. This is what happens inside a star. This is what I was talking about, why fusion power sources are so difficult for us to do, because it literally produces so much heat and takes so much heat and pressure. You have to recreate what happens inside a star, inside like of a small laboratory. which, as you might imagine, is extremely dangerous and hard to do. So it's taken us a long time to get there. But you take deuterium, which is hydrogen that has an extra neutron. So hydrogen should have 1 proton and 1 neutron. No, wait, sorry. Hydrogen that has 1 proton and neutron. I got a little excited with the 2 up there, but that's just 1 proton, 1 neutron. So that's deuterium, can fuse with tritium, which is hydrogen with an extra neutron. There we go. So notice it doesn't have a 2 up here. It has a 3, which means it has 2 neutrons and 1 proton. That's your tritium to form a helium nucleus that has 2 protons and 2 neutrons and shoots out a neutron. So energy and the extra neutron are emitted, and I believe they have a little video here. Yes. Wonderful graphics that you can see here, yes. So your 2 hydrogen atoms, let's replay it for everybody that missed it. 2 hydrogen atoms collide, release a lot of energy. You have helium that's left over. Is helium like a radioactive waste or anything? No, it's helium. Literally, when you get a helium balloon, you breathe it in just for fun. And so hydrogen is also not anything that's bad for us. Obviously, hydrogen can catch fire, like the Zeppelins that caught fire. But definitely way better than like uranium or plutonium or anything like that. So fusion reactions can only occur when 2 smaller nuclei are brought together under extreme heat and pressure, like what happens inside a star. The conditions required for fusion are difficult for humans to produce, obviously, but we are working on it. Fusion reactions only occur in extreme environments, such as the sun and inside nuclear weapons. So when they talk about the H-bomb, that is one that used fusion as opposed to fission. I don't believe, unless I'm mistaken, I don't believe that they were using like uranium or plutonium. I think that they were using fusion reactions to make that happen. So fusion reactions in the sun produce alpha particles, positrons, and energy from 4 hydrogen nuclei. So you take 4 hydrogens, smash them all together, you get a helium and 2 positrons and a whole bunch of energy out of that, which travels all the way through space and hits the Earth and gives us nice sunny days, or in summer makes us miserable. So fission and fusion are opposite processes. In fission, your large nucleus is broken down into smaller nuclei. And fusion, your large nuclei are created by smashing 2 smaller ones together. Both fission and fusion are nuclear processes that produce large amounts of energy and cause formation of new isotopes, which is very important for us. Both fission and fusion can be initiated by scientists, although one of them, fission, is much easier. Fusion, we can do, but we have a lot less control over it, and it's a lot more dangerous. So I believe that's going to be it. Fission chain reactions can be controlled. Fusion chain reactions cannot be controlled or sustained, which is why we don't have fusion power plants, but we do have fission power plants. So that's going to be it. You can go ahead and open up the assignment. Use your little sheet. I will post it on Google Classroom to help you all out if you lose the sheet or you want to look at it later. But if you have any questions, please let me know. Or if you're online still, please send me an email and I will get back to you. Thank you.